Good afternoon to everyone. My name is Annaloro Vincenzo. I work for CS since 15 years now. I'm inside the high-performance computing solution unit. I'm a system manager and currently managing a couple of computing cluster systems, mainly with the goal of supporting visualization activities, general purpose GPU computing, and general pre-post-processing tasks for the Swiss research community. Today I'm going to show you and provide you some installation and operational needs of multi-purpose GPU clusters that we have at CSCS. I will try to bring you a couple of examples of facilities, how we install it, how we operate it, how we daily manage it, and what kind of software requirements and hardware design we choose on these solutions. Let's start with the first facility that a couple of years ago we provided CSCS, we installed at CSCS based on end users' applications requirements and needs. We set up, we design, we procure this cluster that we call EIGER, intended for supporting visualization and research and development GPU services. Today we will see, we'll pass through the agenda. We'll have a quick introduction. We'll have a look to the system description overview, an hardware overview, and also a software middleware infrastructure overview of the entire solution. Then we'll focus a little bit on general purpose GPU computing services provided by the cluster, and of course the remote visualization services. Then we will have a look also to the batch queuing system resource manager that we adopted on these facilities, and we list also some administration and monitoring tools we currently are deploying in order to maintain monitoring and reporting and administering in general the cluster solution. And then we have a list of open issues problems that we are still facing, and we are finding some solution together with our application developer in-house. Okay, let's move on with the presentation. Okay, the second part of the agenda planned initially to present also a new facility that we have just procured at CSCS, and is another general purpose GPU computing cluster based on the NVIDIA architecture Fermi. If we have time, we will see some details about also these facilities. We'll see at the end of the presentation. Let's move on. As I told you, the first cluster is a DALCO visualization research development cluster EIGER. It was the first CSCS GPU production computing facility. It has been introduced and operated in the second quarter of 2010. We integrated it in our CSCS computing ecosystems together with all general services that we provide to our end users base. It has been open to the Swiss scientific community mainly for the following four targets: for visualization and data analysis services. This is the first and the main goal of this cluster. To support remote visualization and collaboration services. To support also hybrid multi-core and multi-vendor GPU computing services. Then we mix GPU architectures inside the clusters, as the guys from ETH. And then also for other general purpose pre-post-processing activity services, mainly supporting some of Metro Swiss climate customers and other guys. The system description: the system is based on a tightly coupled computing cluster system. It's running as an high-speed interconnect and InfiniBand quadrant fabric. It's running the /11 operating system. It provides up to 19 nodes of computing and visualization nodes. The total cluster nodes is up to 25. The remaining nodes are support nodes for services inside the cluster, and are mainly based on AMD Opteron architecture. Inside the cluster, we have a big heterogeneity in terms of GPU architectures. That's surprising because we have let's say, a small cluster system with only up to 19 nodes available to the end users, but we try to provide really and to follow the evolution of the mainly NVIDIA architecture, but we also introduce the latest AMD HD Radeon multi-GPUs cards inside the clusters. Then, as you can see, we have some old GeForce Gaming 3D cards, the early Tesla S1070s, and then we move on with one of the latest Fermi cards, the M2050, the C2070, and recently we have the hands on a new M2090. This means not all cluster nodes provide 1 or 2 GPUs, but we decide how the configuration, the layout of the GPUs inside the nodes will be based on our end user requirements. Then we set up the layout according to them, their requirements. Okay, as I told you, we have essentially, at the level of a cluster network infrastructure, three networks. One is a classical InfiniBand QDR fabric that we mainly use for supporting both parallel MPI traffic that we provide the end user application support via the MVAPIC2 implementation, the OpenMPI implementation for message passing. And the InfiniBand fabric also supports the internal parallel sketch file system. It's a local GPFS sketch file system available only to the cluster nodes. Then there is an additional commodity 10 gigabit Ethernet LAN for login, which ensure login access for users. And then there is also a third network that is used by sys administration for installation and so on, and controlling in general. We design the cluster. We start from creating several classes of nodes. We distinguish administration node, login nodes, visualization node, FAT visualization node. Those nodes would have much more memory. And storage nodes supporting GPFS infrastructure and other pre-production test nodes. The latest one, these pre-production test nodes inside the cluster, are a very important one because we use those two pre-production nodes in order to test any new NVIDIA driver or CUDA level before moving on the production, the new NVIDIA CUDA toolkit infrastructure and so on. This picture just gives you an overview of the cluster. The guy is coming in through the firewall from the switch LAN. Just connect onto the login node. He do his preparation work, setup of jobs, and so on. He submit all his interactive or batch jobs via the Slurm resource manager systems. And these jobs goes on one of these 19 nodes. As you can see, the three LANs are here: the InfiniBand, the internal gigabit administration LAN, and an internal IPMI LAN for the This is my machine, the system management workstations. And you can see here to the right the GPFS infrastructures. It's a 66 terabyte of total formatted storage available as scratch file system inside the cluster for I/O jobs in general. Okay, let's move on. The remote visualization service is one of the most important ones for these clusters. We provide essentially a reduced application portfolio. We give mainly support for ParaView visit applications, but also we have, based on request from the end users, we provide additional applications, standard one, independent software vendor application like Mathematica, MATLAB, and so on, Chimera, some chemistry application, and so on. From time to time, the guys using ParaViews run it as a render farm. They use only the CPU inside the clusters for computation, as a render farm, but we also allow it. What are the key enabling technology allowing the remote visualization to be provided to the end users? We mainly base our services on these four technology. We use the virtual GL, Turbo VNC, Turbo JPEG middleware software infrastructure. We use, of course, the 3D hardware GPU accelerators on the nodes, and we provide OpenGL APIs and libraries and the high-performance interconnect InfiniBand underlying. The virtual GL, this open source software, just allows anyone to do remote OpenGL applications. It's an important piece of software that, in the end, intercepts any OpenGL commands and 3D data and redirect those commands and data on the 3D accelerator, on the node who has really a GPU accelerator cards. Okay, this piece of software, VirtualGL, also allow 3D graphics hardware to be shared among multiple users. Then we will see later how this is possible. Together with VirtualGL, we also use this Turbo VNC, and we also provide these Turbo JPEG libraries for accelerating the compressions. The Turbo VNC is really important for our end users. Since we have many users coming from other universities remotely, they want to run basically OpenGL applications. And thanks to VirtualGL and Turbo VNC, we can ensure that the performance of 3D rendering on the remote nodes passing through the wider network and coming up to him in his office is well adapted, and let's say it can really adjust also the quality based on the bandwidth available. Yeah. Okay, of course, as I said, all the cluster nodes provide different GPU cards, NVIDIA family, and also AMD ATI family, the Radeon cards. The GPU computing services is mainly supported by a couple of software infrastructure provided by the vendor itself, the NVIDIA CUDA, all the NVIDIA CUDA toolkit, the software development kit, and the GPU driver itself. These three elements are essential one for supporting any CUDA development on the clusters. Today we are currently testing with the latest announced driver from NVIDIA, and we run those tests before putting into production using our two pre-production nodes. We ask our application guys to run their GPU benchmarking suite on these cluster nodes, and then if everything is accepted, we move on to the next level of the NVIDIA driver. This is a critical piece of software because it has a big influence on applications, and we saw also the output of the NVIDIA SMI command is always changing when the NVIDIA CUDA toolkit change. It's a different, we face many problems with this. For the AMD Radeon part, we have a couple of nodes providing such performing GPUs, and the software infrastructure we provide our users in order to use and to write OpenCL code version 1.1 is mainly based on the driver itself supporting GPU and this accelerated parallel processing software development kit, together with a couple of mathematical libraries for accelerating the mathematical operation. Then we provide also additional tools for debugging, profiling application for the AMD Radeon GPUs. Okay, let's skip. Okay, the development environment is a critical one. And then for satisfying specific user projects needs, we were forced to purchase a couple of set of licenses from PGI Accelerator in order to take advantage of the accelerator directive provided by the C and the Fortran of the PGI compilers. As you can see, we provide additional compilers in order to, let's say, comparing result, ensuring that the scientific results computed with one compiler also are acceptable. And one important piece of software that we provided is the Eclipse IDE environment for C and C++ development, together with this Eclipse CUDA plugin that really easy the life of our CUDA developers. because they really do their entire development using this tool. We are currently also evaluating some debugging tools, commercial debugging tools like TotalView, that recently has announced the support for the latest version of CUDA, version 4.0. And recently, our application guys finalized the evaluation of this linear DDT debugging tool with CUDA. They are quite satisfied. Then a decision to invest in such technology may be, in the next month, may be implemented. As other debugging tools provided by default by the CUDA environment, you can use the CUDA mem check or other stuff like CUDA debugger. And as you saw before, we provide also the CUDA profiler and the OpenGL profiler for profiling application codes for the end users. There is also a profiler for the ATI Radeon stuff that we provide. As I told you, the visualization, research and development cluster hardware, for the end user, he can access this system through the batch queuing system, the resource manager's LERM. We choose this batch queuing system for this facility essentially for 4 reasons. You can see we decide because we don't have to pay license fee, and then we have also a developer support thanks to our, let's say, privileged link with one of the developers. It's highly customizable, the Slurm interfaces. We can extend via plugin also the functionality of the resource manager. It's already widely adopted inside CSCS on any of the supercomputing facility, and allows us also, let's say, the task placement of MPI task placement inside the cluster. It's very fine grained. We can really define the good geometry of task placement. We can distinguish between sockets, core, where to place the MPI task, in which order to follow, which algorithm to use, and so on. It's very, very customizable, the resource manager's LERM. Okay. As an example of customization, CSCS has already customized as LERM for its needs, introducing the budget-based CPU accounting priority scheduling. Okay, today we are not yet able to support the GPU job accounting. Let's say there is no budget that limit end users to using GPU, and then because we cannot yet account GPU, the real GPU usage. That's another story compared to the nominal. This picture just shows you how the Slurm resource manager is configured for this visualization facility. As you can see, there are essentially 4 partitions defined inside Slurm, distinguished by wall time and the number of visualization nodes you can access. The end user simply submit their Slurm job using the classical sbatch, srun, or salloc Slurm command. And within the job specification inside the sbatch directive of Slurm, it simply can specify this keyword gres and the constraint keyboard for making the scheduling according to their desire. This means it can ask for 0 GPU, 1 GPU, 2 GPU, or for any other of these keywords defined here in this list. And then it can go on the appropriate node with 1 or 2 GPUs, or maybe he wants just one node, a full node with a Radeon, and so on. It can combine the selection. Of course, in this cluster, we also allow mixing job inside the same node. The node is shared for multiple end user jobs. And those jobs can also take advantage of the GPU acceleration or not. They can do classical MPI jobs. They can do mixed hybrid MPI CUDA jobs, and so on, or simple serial jobs. It depends. Here you can see the third partition is a test partition that allows our internal developer to test many of the new features before putting in production the final configuration. Yeah. What we use today for managing, installing, configuring, profiling our clusters, we use classical tools provided by the operating system itself, like the AutoYast, and all the standard services like the HCP, BootP, TFTP protocol, PXE, boot protocol, and so on, for the installation phase and profiling phases. On a daily basis, we just administer a cluster using C-thread tools, these parallel distributed shell tools, and so on. For getting information about the status and report of GPU on any of the different visualization nodes, we use the NVIDIA command, the NVIDIA SMI command, and the ATI config command. Based on the output of those commands, we may implement some action to correct some problems that we can detect. For the cluster file manager, we decided, because of the heterogeneity of the cluster in terms of GPU architecture, and in terms of also of CPU architecture, because we also provide different kind of AMD architectures, many cores as in Istanbul, we decide finally to implement and support the Puppet cluster file manager in order to keep in sync and coherent status any cluster nodes. Another important tool that we look on a daily basis is the Gallium monitoring tool. We simply use the NVIDIA SMI commands. We just run it on a 1-minute pollings on any GPU nodes, and we grab this information. The GPU temperature, the fan usage, the memory usage for the GPU, and the GPU core usage in percentage of the total GPU cores available on a node. And also how many end-user processes are currently using the GPUs. Yeah, as you can see, these are two snapshots of these graphics. Was a temperature of GPU 0 on these EIGER 220 nodes, and so on. You can see a small variation here. And that guy was running on this node, yeah, at some time. Then he stopped, then he restart. The process is accessing the NVIDIA driver, and so on. Another interesting tools, this is a critical one, is Nagios. We integrated in Nagios some periodical critical check, because we noticed in the last 1 year and a half that, let's say, the ATI drivers are not so stable. And then when they crash, you are forced really to restart the entire node. Also the NVIDIA driver, even the latest one, when users start doing some MPI CUDA debugging, we face many, many problems. This means the driver crashed completely, and the only solution for us is to restart the whole node. Then we need absolutely to detect this bad status and to recover it. And for this reason, we integrated into the Nagios, this monitoring tool, essentially, many, let's say, periodical checks. Then we have some status about the clusters. Okay, today we have a couple of open issues still on these facilities that we are trying to solve ourselves, or we get in touch with NVIDIA directly also. We would like, for instance, to have an automatic and transparent self-recovery after any NVIDIA or AMD Radeon driver failure. Okay, this is also a research topic. We would like to understand how we can really grab a real GPU accounting information and create automatic report, because what we do now today is simply run the NVIDIA SMI like any others, and that's not enough, because we need real information about GPU usage. We want to know really if a user job is using the whole number of GPU cores on these particular GPUs, how much amount of GPU memory is using, and for how long, and so on. Because we really need to understand our user base, what kind of usage they have for the GPU. Other open points, then we face some real problems when we try to use on a single node multi-vendor GPU coexistence And we place several NVIDIA and several AMD ATI GPUs together, and we will try to use the CPU core, the NVIDIA GPU cores, and the NVIDIA Radeon cores together in these hybrid programming languages. But we face many crashes. It's, if you go in depth, and immediately you realize that AMD Radeon, AMD will not allow you to install NVIDIA together in the same system and so on. But we do this experiment because we want to understand if this is true or not. But we face a real problem. Okay, some other small features that we would like to have, for instance, it's the runtime limitation on GPU kernel should be disabled for NVIDIA GPUs. And this is not always true. If you check with device properties and so on, you can find this flag activate or disable depending on the capability of the GPU itself, if it is a Fermi or not, if it is the latest Fermi generation, or and so on, depending on the capability of the GPU. Yeah. We would like also to have the concurrent GPU kernel execution should be allowed for NVIDIA GPUs. That is not the case for our configuration. And then one important thing, we would like to have our end user jobs to be able to directly enable or disable the ACC GPU memory control inside the job itself. Because maybe the users would like to take advantage of the whole amount of GPU memories available on the cards, because activating the ACC GPU features, as is by default on Fermi cards, for instance, take away, let's say, a consistent part of GPU memory available to the end user job. And that's a feature that we want to ask to NVIDIA to be able to do it at the user level. This is possible only at root level. And the same thing is for the GPU computer operating mode. You can change the GPU computing operating mode only as root user and not as end user. Yeah. Okay. I think we have still some time. Yeah, perfect.
Well, actually,
yeah.
In theory, you could change it as a non-user. You just need that right permission to the dev NVIDIA devices. And you need to trick CUDA into thinking that you're...
Okay. Because on CUDA 4.0, only root can do this.
Yeah, because
or,
but the communication between the user line and the kernel is always with these dev NVIDIA devices. First you need to be able to write to it, and then you just need to know what to write. There's an internal check
okay.
itself.
Yeah. Okay, let's move on to the second part of the presentation. We'll see what these new facilities that we have just received last week. It's currently under physical installation in the CSCS machine rooms. And this was designed because of a CSCS project together with external partners, external commercial partners also. And this facility is mainly meant for CUDA GPU development, essentially, and other related projects we will see later. As I told you, CSCS, together with several academic and industrial partners, want to evaluate essentially these two milestones. You want to evaluate interconnect virtualization for scalable heterogeneous hybrid multi-GPU platform, and you want to provide for a subset of hpc projects early access to a representative GPU prototype systems. The project goals are to try to improve the efficiency of hybrid application by reducing the communication overhead between GPU devices, and this using the GPU direct technology. The second important goal of the projects is to try to assess the feasibility of completely decoupling GPU and CPU resources in an hybrid computing environment. This will be done extending the ERCUDA framework. And the third goal of this project is to evaluate scalable interconnecting technology using industry standard components. Essentially, we want here to evaluate InfiniBand fabric topologies, different InfiniBand topologies inside a cluster. As an high-speed interconnect, we want to prove whether a 2D mesh or a 2D torus or a 3D torus topology would be better for a particular kind of applications. All these project goals led to the purchase of this cluster system that I'm going to present you now. Okay, let's have a look quickly to the phases of the project. The project has been divided into two big phases. The first phase will run from October this month until April 2012. And then the second phase will start after April, after we move to the new building, and will end by December 2012. Yeah. Okay. This system that we just received last week, we call it CASTOR, is essentially a GPU cluster. It has, let's say, it will be installed in 1 month. It will be operating and open to the internal CSCS projects. It's essentially formed by 32 IBM DIX 360 nodes. It's an Intel-based cluster servers and has only NVIDIA M2090 GPUs, 2 GPUs per node. Okay. The system, the IBM IDataPlex cluster, will be finally partitioned in 2 subclusters because to support and implement some of the project needs, we really need to subdivide the cluster into distinguished clusters. Otherwise, there will be really conflicts. Okay. As I told you, one of the main objectives of the project was or is to understand what kind of high-performance interconnect topologies based on the current InfiniBand fabric infrastructure are better for a particular set of applications. On these particular goals, our application specialists will going to implement, let's say, several test suites to demonstrate whether one particular application scales better using a particular topologies or another one, based on different cases. And the topology we are going to test will be, as I told you before, the simple 2D mesh, the first one, and then we will go up to the 2D torus, a standard 2D torus, and a 3D torus topologies. To implement this, we just bought 16 InfiniBand switches that we are going to connect together to build up these simple topologies and start doing our first test. Okay, just simply, the cluster networks available are this particular InfiniBand QDR fabric with 16 InfiniBand switches. Then there is also a more standard InfiniBand QDR fabric topologies, a simple one using only one switch. On this second InfiniBand infrastructure, a GPFS cache file system will also be run in order to support fast I/O performance for end-user jobs. And we have next to it just a commodity gigabit network for installation, for administration in general. This picture gives you an overview of the two, let's say, the two partitions of the whole solution. We have, as usual, a GPFS installation here, providing some row spaces to the whole clusters through the first InfiniBand networks. And then we also have the other networks here. You can see, you can distinguish the two partitions. And on the second partition, the Pollux partition, most of the goals will be implemented, the project goals. The first partition will be mainly dedicated to the hpc project And the second one, we really do some experimental tests on this partition here. Okay, inside the cluster, we are going to run the Red Hat Enterprise Linux as an operating system. We will manage it via the XCAT management system and through standard administration tool like Paradistributed Shell, Cluster File Manager. We are going to use Puppet and other standard monitoring tools like Ganlia, Negus, and so on. Also here, on this facility, we are going to provide the Eclipse integrated development environment for easy the life to CUDA developers, of course. And also, the development environment will also include many of the available compilers from PGI, from Intel, and the Open64, Patscale, and the standard GCC compilers, together with some of debugging tools that we choose. Okay. Okay. One important thing is that we are going to provide both support for all these compiler combination between the NPI implementation and the compiler for both MVAPIC2 and OpenMPI implementation. That's important because one of these MPI implementation allows us to define at configuration time also the topology we are going to run on. And for MPI task, for our test, it's really important. Also, Slurm is used on these facilities, as the previous one you saw before. GPFS also. Okay, now let's see the main software infrastructure that the application guys are going to test, to install, configure, and extend. Also, they are going to do some development stuff for this software infrastructure. The first one is the RCUDA framework. This framework essentially enables the concurrent usage of CUDA-compatible devices remotely inside the clusters, and could be useful for reducing the number of GPUs installed inside a big high-performance computing GPU clusters. Imagine you have to invest millions of Swiss francs, and then you are not really so sure that all the nodes must have a GPU provided inside this cluster, because also it could cost you a lot. Then having this capability could be interesting also to reduce the total number of GPU available inside these systems. Okay, for other stuff. The second software that is going to be installed in the second partition of the cluster and to be tested and evaluated will be the MOSIC Virtual OpenCL software infrastructures. Another important technology that we are going to test is some early release of the GPU Direct features available through Mellanox and NVIDIA. Today, the GPU Direct technology is provided directly by the CUDA 4.0 and the corresponding Mellanox and QLogic InfiniBand driver. With this technology, it's important for those that are running MPI CUDA task on GPU clusters, because it allows you to share memory between NVIDIA GPU and the Mellanox host InfiniBand adapters or the QLogic InfiniBand adapters, and speed up the movement of data copy between the GPU memory and the buffer inside the InfiniBand adapters. And this is a key point when you have to move data between, of course, GPU memory on a node and the GPU memory on another node. This operation will be accelerated. Today, we have this architecture provided by the CUDA 4.0 and the corresponding Mellanox and QLogic InfiniBand drivers. When you want to move some data from the GPU memory and going outside on another node, usually you have to pass through all these components, and these add delays, of course, latency, and so on. And you have to copy the data in the main memory of the host once to a second buffer, second zone of memory, and then take this part of memory and copy it on the buffer of the InfiniBand driver and move it outside on the network to the next node. Today, with the GPU direct technology, you just go directly. You skip one step. You don't create two distinguished memory zones, but you use only one. Oops. You use only one, as you can see here. Use this same memory zone to copy the GPU memory data there, and this same memory zone will be used to be copied inside the buffer of the InfiniBand adapters and move on to the next node. Yeah. Our application developers will, together with NVIDIA, are going to investigate the next step of the GPU direct technologies, and these tests will be done on the second partition of our CASTOR GPU clusters. Yeah. Okay, that's all.